Today we're going to be doing a credit card fraud detection using Python. Now links to the notebook, the dataset and this website here will all be found down below for absolutely free. So let's begin. Now taking a look at this dataset, which again you'll find included within these three files below, you'll find that it's a massively popular dataset with a really high usability score at 8.53. but closing in on 5,000 people contributing various scripts, as well as hundreds of people discussing it. And so with that, let's begin. Now, for a little bit of context here, you can see that this is credit card fraud. Now, they have anonymized the variables here, so it says V1, V2, and so forth. Some of them, it will tell you what it is, such as time. And equally from this, we'll be able to tell or predict what is fraud going forwards. Now I'll show you exactly what that means and how to do it. To get started, make sure you just hit download over here. But let's begin. Now I'm going to be doing this in Python, but specifically within the IDE of Jupyter Notebook, which is very common for data science. Now to get that, right click, open your terminal in the same location which your dataset is in, and you're going to want to type pip install Jupyter Notebook. Now I already have Jupyter Notebook, so you'll see here it'll say requirement already satisfied. There we go. So let's allow that to run for a moment. If you want to see what version of Jupyter Notebook you're on, or just to check it works at all, let's just run it here. So now you've installed it, just type Jupyter Notebook, and this will take you into the environment. Now it's a web-based application, so if you're not familiar with it, don't worry, we'll explain it all here. Now, as I said, the entire notebook or script, this .ipynb file, I've already done. So let's open that up. And you can see here, in just a moment, everything is explained in a lot of detail with these code comments. So yes, this script is for exploring the credit card fraud detection using pandas, Matplotlib and Seaborn. It'll cover data loading, performing EDA, and building a random classification model, which is a type of a machine learning algorithm. Here's again where you'll find the dataset. Now, again, it is anonymized, but it is labeled as either fraudulent or genuine. We can take these classes with a value of 1 if it's fraud, and it'll be 0 if otherwise. That's here. Again, we can use all of this classification data, all this historical data to predict cases of fraud in the future. So first off, we're going to want to import all the necessary libraries. That being pandas for data frame manipulation, NumPy for numerical computations, Matplotlib for visualizations, Seaborn for building on that with statistical plotting, and then we'll be using sklearn, also known as scikit-learn, for our machine learning. We're going to want to train test split, the actual model, and then metrics to evaluate it. We've gone with these three here. Don't worry about that just yet. We'll get into that shortly. But first of all, let's really load in that data set. So what I'm going to do here is using pandas, which you can see I've called PD here. That's what I referred to as earlier, which is common convention. I'm going to read the CSV file, credit card, which we just downloaded, and store that under the variable df. What I'll then do is call df.head, and this will load the first 5 rows. So let's hit shift and enter, or equally you can hit run up here. Now the reason that hasn't worked is because we didn't actually run the cell here to import the libraries. So let's allow it to do that. And you need to ensure you do this each time you're using it within a new notebook. There we go, you can see it's loaded for the second time. And now when we press shift enter, it will run. So these are all the rows. It's important to know in Python, indexing starts at 0. So there are 5 rows here, although it starts at 0. Now these are all the columns. We've been over the fact that it's anonymized. You can see there are 31 columns, which is very impressive. How many rows are there? Well, typing df.shape, and you don't need to follow this method by any brackets, will tell you there's an absolute huge amount. You can see there's thousands and thousands of rows. It's really quite impressive. So this is going to give us a really accurate model. Generally, the more data you have, the more accurate it is. Now, if we run df.info, that's the information about the data frame. And running that, again, you can either do by pressing this up here, which is very quick, or Shift and Enter as a shortcut. We'll tell you for each of these columns if there are any null values. So we can go through them and see, no, this is how many non-null values there are. These are all float values. Float values is where there's a decimal place. Integer would be a whole number, like 1 or 0, which is the case here. Fantastic. I did want to see if overall there were any null values, and I was missing it when I was going through here. There isn't. Now, the reason I put the additional .sum at the end is if you just run it like this, it'll tell you for each column how many null values there are. Whereas I wanted a total sum, and I can see, in fact, there are none. There are quite a few duplicated rows. Instead of dataframe.isNullSum, I ran dataframe.duplicated.sum. And it tells me there's 1081 duplicated rows. Now, what am I going to do about that? I actually don't have the domain context to know whether that's expected. I could drop these. I could try and look into whether that's required or if it's not needed at all. But again, as I don't know, I'm just going to leave them, because it could be that they're there for a reason. But then something very important, which is often overlooked, is the distribution of the classes. Now, in classes, I'm referring to these here, the very final column. That is 0 or 1. Remember, 1 being if something is fraud and 0 otherwise, so no fraud. Now, is it about equal? So what I did is created a variable called class counts, and I set that equal to the class column. Now, if I wanted to take a look at that column, what I could do is just type df class, which is the name of the column, and it will show me all the rows. I could write .sum and run various other methods on that as well. That's adding up all the values. I could do mean and otherwise. So what I'm doing is calling that column as I just did, but looking at the value counts, which is 1 and 0. What I then want to do is plot that distribution. Now I'm setting the figure size, which will be how big the plot is. You don't have to set that, but often if you don't, it's a little bit too squished or even too big. Then I'm creating a bar plot. Using this class counts, it's going to use a color palette as well here, just to make it look a little nicer. It's going to give it a title, label the X and the Y axis. And then it's going to label 0 and 1 and replace that with not fraud and fraud. So running this cell, we can see here there's a massive, it's not equal. There's a massive number of not fraud and very little fraud, which is good. We should be glad that there's not too much fraud within this if we're looking at this as someone working within the organization. However, for us running the machine learning algorithm, it's not necessarily a great thing. There's only 492 cases of fraud. We want to make sure this is as even and standardized as possible. So it's just something to bear in mind. Now back to the figure plots, the figure size. We could delete that and run it. And you can see it's just a little bit squished. In this case, it looks fine. We even might want to bring it down a little bit as well. But let's replace that. Again, if you were to remove these labels, it just wouldn't necessarily be too clear what it was. Hence, we leave it in there. Now, there's another plot down here which I found very interesting. We wanted to look at the distribution between the classes 0 and 1 over time. So again, we set the figure size, and let me show you what it's like if you don't do that. It's very squished here. So we set the figure size. This time we did a his plot, which is a bit like a bar chart, but it's in various bins. Now, in using bins, it groups data points together. We looked at time, and our hue, which is our legend here, is the class. This is what it's going to use for the colorization. Now, let's run that, which we can do Shift Enter. You can see here that the transaction time distribution, as time goes on, and this is time in seconds, which we'll take a look at in a moment, because it's not particularly helpful. At this particular time in the day, there's quite a lot of class 1, not many class 0. You can see this pattern throughout the day, but we don't want it in seconds. We'd much rather have it in hours. And that's where feature engineering comes into effect. We need to create or modify a column to get something we need. So we're going to create an hour from time, which is in seconds. So to convert time from seconds to hours, we're going to divide it by the integer of 3,600, because that's how many seconds are in an hour. So we're creating a new column called hour in the data frame, and we're setting that equal to time divided by 3,600, no decimal places. And what we're going to do with that, and this is where it gets a little bit complicated. And so what I've done here is I've left a lot of comments and really broken it down for you. So let's take it one step at a time. We're going to aggregate the transactions data by hours and class, fraud or not, to calculate various statistics, such as the sum, mean, median, the variance, the max, and we're going to use reset index as well, just to flatten the data frame. Now, to explain that, and don't worry about it too much, is we converted this into a multi-level index by combining and aggregating these variables. We just want to put it back into a normal table structure that is easy to work with and you'll be more familiar with, like that which we'd seen above in the head of the data frame here. So once we've done that, and that's what this line is doing, we're then defining a function. Now, it is great to make sure you do have Python fundamentals down. It is great working with data analysis in Python, but you don't want to lose track of features such as functions. Now, a function means you can call it later in the script. Here, we're defining a function called plot hourly aggregation, and this takes in the metrics, which is the sum, median, all of these from earlier, and then the title. We set a figure size. We create a line plot. We then give our typical labels and we give it a legend, and we can then call that function later. This makes it a lot more condensed and we're not repeating ourselves. So we call that plot hourly aggregation function on the sum, the count and the mean, and we give it a title. As we said here, you have a function, you state the metric and then the title. And upon running that, we can again look at the distribution over hours, which is a lot more useful than seconds. As you can imagine, that's very granular. So typically, it's class 0 is most common when we're looking at per hour. Not surprising. Again, here. But when we look at the average transactions per hour, you can see that it does peak more often. It's more stable with class 0. But class 1 does peak at various hours in the day. Now, this might not be particularly useful to you, but it's always good to do this process of EDA, Exploratory Data Analysis. And I do encourage you to download this notebook. Take a look at what other people have done as well. They've got some fantastic code here. If you rate it by the most votes, you can see this has over 5,000 upvotes. It's rated as gold, and this again deals with this imbalanced data set. A lot of these I'm noticing do deal with the outliers and the skewed data in the classification problem, which we'll get to in a moment. Now, as I said, Seaborn is more for statistical advanced plotting. We can do things with that, such as a correlation matrix, a heat map. So we set the figure size, we're very used to that now, and we're going to assign the correlation matrix on the data frame to the variable core. Then with Seaborn, we can set a heat map, and just a quick trick here, when you type SNS calling Seaborn dot and then hit tab, it will actually give you a list of all the different functions and methods that you can call on it. One of these being, if you start to type it in, heat map. So we're calling a heat map on this variable here. And not equals false. I'm actually going to change that here to true. You'll see the difference in a moment. It'll add data labels. CMap cool warm. That just means it goes from blue to red. So an absolute relationship, correlation, and none at all. Then the line width, which is again just to do with how visual it looks. Give it a title and let's hit enter. And now you should see it looks very similar to how it did previously, but we have these, which aren't distributed very evenly. It doesn't look great. Let's turn it back to false. When there's only a few values in here and it's more evenly distributed, it's a lot easier to have a knot in there. Now, of course, everything is 100% correlated with itself. That's why we've got this diagonal line going through. Some things are very uncorrelated, V3 and time. Some things slightly more, V7 and amount. Now that's interesting to see. We don't know what V7 is, but we can see that it has a very positive relationship with each other. Same here, V20 and amount have a very positive relationship with one another. Now going forwards, we're actually going to get into the machine learning. Now this is where it starts to get a little bit more complex. So let's just recap what we've done so far. What we did is we looked at this data set. We had a look at the different rows and columns. We saw it's actually quite a huge data set with no null values, very clean. We did note though that the class distribution is very uneven. So we can see there's a lot of non-fraud to fraud, which is good, but again, difficult for us going forwards. We looked at the transactions over time. We even looked at functions and how you can pass different variables into that as well. We created a new column with feature engineering called hour, taking the time and dividing it by 3,600. And then we set it to type integer here as well. This means we can have a play with it and have a look at the feature correlation matrix in Seaborn. And that brings us to here. Now, the way that machine learning works very quickly is there's a bunch of different models you can use. The one we're going to use here is a random classification model. Now, to give you a bit of insight into how that works, let's just find a good visual for you. Now, if we head over here, you can see their official documentation is right there, scikit-learn. That's their own website. Now, it works just like this. It'll take a look at your features. Now, we'll assign the X later. And this is a little bit complex. But very simply, it looks at something, it assigns different weights, and it thinks, is it this or this? Oh, it's this. Is it this or this? Then it's this. And it aggregates that over multiple trees. A decision tree is where there's only one of these. A random forest is where there's multiple of them. So bear this visual in mind, and then a decision tree is just one. So for example, if you wanted to take a look at this, see someone's age. Are they less than 18 or greater than 30? Oh, well, actually they're 18 to 30, so they're lower risk. Are they greater than 30? Well, are they a smoker? Well, no, they're low risk. So that's what I'm trying to get at. It has many of those, all looking at different elements of the data set. It aggregates the results together to get a more accurate picture. Now here, it's going to be using the different variables, and instead of these labels, it's going to say, is it fraud or not? Well, is V1 true or false? V1 is false, so here. Is V2 in effect? And it's going to be very large across multiple trees. Now, I understand that wasn't the best explanation, so I hope it gave a little bit of insight there. And I do highly recommend looking up the own sklearn documentation. So that's how that model works specifically. In terms of more generally, machine learning, it works by splitting the data into a training and a test set, which is why earlier we had imported this train test split alongside the model, which I just spoke about, and then the metrics. It breaks the data set into two halves. A training set, it goes through all of this historical data and looks at it and says, okay, well, when V8 was this high and V21 was this low, then was it fraud? Yes, okay, so, and it builds this picture. And then it tests itself on its presumptions and it goes, okay, so given all these features, I think it was class 0. Was it? Brilliant, it was. And that's actually how we can evaluate it. So we can then look at all the times it got itself right and say, oh, I was right 60% of the time. I have a 60% accuracy score. Now we want to dedicate the majority of the data to the training set to make sure it builds a better picture. So typically we save about, let's say, 20% to test itself on and 80% to train it. So we can see that we will have done that down here. Now, before we even get to that, because you can see we did in fact set 20% to the test size, We need to say what we're even looking at, which is those x variables which I had referenced earlier. Now, x is everything aside from class, which was the binary classification. Was it fraud or not? Y is the class. So it's going to look at everything, all of those columns, to determine the class. That should help it build a better picture. Now, we're going to split the data. To write this, it's a little bit strange in how it's done. It's not so straightforward. You have to write xtrain, xtest. They're both the x's, and then both the y's is ytrain, ytest. Train test, train test. It's just the order you write it in. But anyway, what this is the train test split, taking in the x and y. It's convention to write x in uppercase, just bear that in mind, and y in lower. We want to specify to this algorithm that yes, we are looking at 20% to test it, and then random state. This parameter just means that every time you run it, you get the exact same result, always. This number could be anything. It can be 42, 53, 106, it doesn't matter. But so long as you run this with the same random state as I do, and the same parameters, it will give you the exact same result. So it's useful for cases like this, but we're trying to match each other up exactly. Then I want to initialize the Random Forest Classification model. So I have the model here, and I assigned it to Random Forest Classifier. So then I can call this variable of model later. And you can call this whatever you want. It doesn't matter. Here I've just called it model. But we want to train the model on the training data. So I fit the model, or the Random Forest Classifier, to the train and the train from both the x and the y. See, we split it into 4 sets here. Then we're able to make our prediction for the class, the y variable. So our y prediction is the model predicting on the test data. And we're done. You've actually done it now. All that's left is to evaluate it. Now, there's a few different metrics we can use. You see, earlier we imported 3 at the very beginning with all of our imports. We had classification report, confusion matrix, and accuracy score. Now, what I'm going to do is I'm going to run the confusion matrix on the y test and the y predict. Same again for the classification report, and same again for the accuracy score. And let's run that with Shift Enter. It will actually take some time. Particularly, as I said, this is a very big model. It's not looking at just one decision tree. It's a lot of trees. What we haven't done here is standardize the variables. That's important. You can see a lot of people have dealt very well with the imbalanced data sets. So I've left this to them. I want you to go and explore their data, see how it's been skewed and how they've resolved it, and improve that in this data set yourself. So let's allow that to run. Now, previously, when I had the random state as whatever it was before, these were the outcomes. It did very well. It said in the confusion matrix, which again will make more sense when you see it, that 69 correctly predicted as 1, that's a true positive, and all of these, let's just run that, was correctly predicted as class 0. False positives were only 3. It only incorrectly predicted class 1 3 times. And so forth. Then in the classification report, we found a precision of 1. 100%. All predictions for class 0 were correct. Recall 1, 100%. All actual class 0 instances were correctly identified, and so forth. The accuracy score was very high. You can see it was 99%, which is incredible. The precision was 96, which means 96% of its predictions for class 1 were correct. So this is very good. Now, there's a few elements of machine learning which are important to bear in mind, particularly when you get these very high scores. There's a concept called over and underfitting. Now, we are really getting into the nitty-gritty of it now, but let's just look at overfitting machine learning. Here we go. So overfitting is a common issue where the model fits too closely to its training data rather than generalizing. What that means is that it looks at this data and all of these variables, and it's very good at predicting for this data set. Well, in the future, if I use this model to predict on someone else's data, it might not be so good. The reason I Googled this is because I wanted to find a good visual, just like this. So, if it's overfitting, it's really going through each of the data points, which if I was then to copy and paste this on another model, effectively, well, it wouldn't be so good. This is more optimal, just a straight line going straight through each class, class 1 and 2. You can see here again. Now let's see if that has run. It's still running, so we'll allow that to do that. And while that is doing that, I'd like to take a quick look at my GitHub. Now, my GitHub page is not that. It's GitHub. It is here. Toby's Data Digest, and link will be below. So I've got a lot of data here. You can see I only just recently uploaded an end-to-end data analysis project. I've done a variety of different projects. I mean, going far back as 9 months. So there's a lot here that you can take a lot of value from. But this is only the very beginning. Because if you go to my own website, Toby's Data Digest here at tobygeeson.com, we can see there I am. You can access all of my projects, all of my own genuine personal portfolio. And you can see exactly all the projects that I have to land myself jobs that I enjoy working on, using Power BI, using Python as well. And if you wanted to look at more educational workbooks, you can download them here. You guys have loved this machine learning workbook here. It goes into a lot more depth. It's like what we've been working on today, but for loads of models. We're talking regression, decision trees, SVM, support vector machines, and more. With Power BI templates, I even built an app. And if you're not sure how to use any of this, well, there's a video right there explaining it. So I'd highly recommend checking that out. If you want to reach out to me personally, again, on my home, I have my own LinkedIn too. Now, this is going to take a while to run. So I recommend you go take a look at it yourself on my GitHub page, run it, see what results you get. Now, all the very best and good luck.